Okay, kids, so we're back looking at these interesting situations when we try to observe quantities like time, length, and momentum from a reference frame that is moving at a constant velocity with respect to where the object is or the event is that you want to measure. So the first one is time dilation. And here's the equation. I hope you watched the video already from that series from Caltech. They do a really good job. And then also give you some reading to do. But here is the situation here. We have delta TS here in the equation, and this is time measured by an observer that is stationary relative to the time event. So the time events could be something going on and off. It could be a clock going through its normal cycle. Okay, and then delta Tm is the time measured by an observer that is moving with the speed v, so you see the speed v in here, relative to the time events. And the time event could be something going on and off. It could be a clock running, anything like that. And in the denominator here, we have root 1 minus v squared, which is the speed of that frame of reference, all over c squared, where c squared is the speed of light. So here's an example. Let's say we got a clock moving, and here's an observer, and the observer is moving with the spaceship. So the observer is at rest to the clock, and the observer observes 1 hour to go by on this clock. And then someone here is not the observer and is watching this, getting information about what's happening here. And let's say the spaceship with the clock is moving at 9/10 the speed of light, so that's very fast. So you would plug that into the equation here. You would plug that into the equation here. You put an hour in for the time being measured by the observer that's stationary with respect to the events. You would plug in zero point 0.9 here. You do your math. You get 0.436. And the observer measures that 2.36 hours have gone by observing that clock, not the 1 hour. So there's an example of time dilation. The next one here is length contraction. And we have this equation here, Lm is equal to Ls, then root 1 minus v squared over c squared. Similar, you've seen this in the denominator before. So Ls is the proper length. It's measured by an observer at rest with respect to what's being observed. So you might, I don't know, measure the width of a book. Well, if you're measuring the width of a book and you are not moving with respect to the book, you'd be measuring Ls, proper length. Lm is measured by the observer that is moving at speed v with respect to the length. So you'd be trying to measure a book while you're moving past the book. So you might send out, I don't know, radar waves or laser waves or something to get information about where it begins and ends and things like that. But you would have some type of sensor to be able to measure the width of the book as you were moving with respect to the book. So let's do an example. Here's a meter stick. So a meter stick's a meter long. And let's say this meter stick is moving at a constant speed of 0.90 c, so 9/10 the speed of light. Pretty fast. So here's the observer looking at this meter stick fly by. Well, what would be the measured length by the observer? Well, we would use the equation I talked to you about. We would plug in the value, right? 1 meter is the proper length, and it would only be 0.436 meters according to this observer's observation. So there's an example of length contraction. Then the textbook goes into the idea of relativistic momentum, which is a pretty complex topic, but they've decided to put it in. The classical or Newtonian or non-relativistic momentum is the equation you know before. That's the standard equation. We've used it many times. Momentum is mass times the uh, speed or velocity, I should say, of the object. Here I'm just doing the scalar version of it. Relativistic momentum, right here, you take that mass times the velocity and you divide it by that familiar root in the bottom. Now, the derivation for this is quite tough, like I said, but they've decided to put this in the textbook, so here we go. So let's say you have a 1 kilogram ball here. Here it is, 1 kilogram ball, and it's moving at 9/10 the speed of light. So 9/10 the speed of light would be 2.7 times 10 to the 8 meters per second. So the non-relativistic, the classical Newtonian momentum would be the standard, and we're just doing the magnitude here. Mass times velocity And there you have it. Now, the relativistic momentum, you take that quantity and you divide it by that standard root, 1 minus v squared over c squared. I'm using zero point 0.9 all the time just for convenience sakes. So it's moving at 9/10 the speed of light. And look at the momentum here. Look at this difference. Okay, so definitely there's been an increase in momentum. So there's a couple of examples. I hope you read the textbook. Like I said, we're just trying to hit the highlights here. We're quickly running out of time. So I'm more interested in just trying to expose you to some of these ideas in the hopes that if you see them again in a next course, at least you will have an idea of what they are and it won't be the first time you see it. Okay, have a great day. Bye-bye.